Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to a combination spectral session here. We got 3 spectra and we are going to find a structure for the molecule that they all 3 represent using the 3 spectra and the 3 spectra alone. So we have a mass spec, an infrared and an NMR spectra. The mass spec is mainly used for finding the molecular formula. Find molecular formula. The infrared is mainly used to find functional groups, as we saw earlier. Find functional groups. Is it an alcohol? Is it a alkyne? Is it an amine? What is it? And the third one, NMR, typically we do this at the very end, is to lay out the exact skeletal structure of the molecule. And there would only be one possibility. So let's start at the beginning, at the mass spec. How do you find the molecular formula given a mass spec? We said there were 2 methods earlier. Method 1 is using the formula. And the formula is the relative abundance or intensity, and I will just put percentage m+1 peak over the relative abundance of the M peak times 100 over 1.08 is going to give you the number of carbon atoms. Let's see if this works out. So the machine, the printer would typically spit out the numbers here. It's kind of hard to do it using this, on the screen, but if you take the printout, you could find the percentages. So this is going to be 3 over 36 approximately times 100 over 1.08. It's about 7.7. So this is the number of carbon atoms. Obviously can be a fraction because it's a number, so and therefore you can't have any sig figs on that. That's going to be 8 carbons. All right, so 8 carbons. That seems like a very large number for 8 carbons, 136, because 8 carbons would just be 96, and you can't have, 40 hydrogens. So, let's use the second method and see if that makes any sense. Let's do the second method here, method 2. We went over this in our previous video. Method 2 is just trying to fit the number of carbons possible for this molecular weight of the molecule. So molecular weight peak or M plus peak divided by 12 gives us an approximate number of carbons, and then you kind of finagle with that and try to get to a realistic number. So here's 136 divided by 12. That is going to give us 11.3. And so, you can't have a fractional number of carbons. Let's say about 11 carbons, okay? There's a 2 to find number of carbons. So if it's 11 carbons, so 11, let's say 11 times 12 AMU is about 132 AMU. So if you had 11 carbons, then you should have 4 hydrogens, which is kind of an absurd structure. So let's drop it down. So this is not correct. Could it be 10? So let's drop it down to 10 carbons. So if you, let's say 10 carbons, that is going to be AMU. That's going to be 120 AMU, but we have 136, so it's going to be C10 and H16. That could be a possibility. Let's see what else is possible. Our method 1 says there are 8 carbons. 10 carbons seems, that's like 2 carbons more. At this point, we really can't go further. So let's look at the infrared to see if you can find some clues as to what else is in the molecule. Let's take the infrared here. The infrared spectra has a huge, very broad peak here. And we talked about this, I think, a little too much last time. The carboxylic acid peaks are the ones that have this very broad 2,500 to 3,500 or 600 about peak, very broad. It says noodle, and that's really characteristic of carboxylic acid in kind of a paraffin-like solvent. In addition, we have a very strong peak around 1,700 here, and so that is also giving us a clue that this is not an alcohol broadening, but it's a carboxylic acid broadening. So IR information tells us the functional group is a carboxylic acid because we see a 2,500 to 3,500 broad peak, and we see a 1,700 for a carbonyl. And that is for the carbonyl of the carboxylic acid here. Both of these indicate we have a carboxylic acid. What would that tell us about the structure then? That means we don't have C10H16. We have two oxygens in here. So in the 132, we have to subtract the two oxygens on your 136 minus the 32 for the oxygens. This is the M minus O2. And that is going to give us a 104 AMU. Now, if you take this, well, let's see how many carbons we can fit in there. So if you take 104, 104 divided by 12 gives us 8.7. So that's approximately 9 carbons, but that would be 9 times 12 AMU would need 108. So therefore, this is not going to work. We have to have fewer carbons. So if you, let's say, drop this down to C8, then you would have 8 times 12 is going to be 96. And that would make more sense. So we can find the number of hydrogens. Let's say this is M. Hydrogen is going to be M. And this is going to be 136 according to our graph. So 136 is going to be equal to 8 times 12, 96, plus 2 times 16, 32. And let's say this is, we don't know how many, let's say this is M. And therefore, M is going to be 136 minus 96 plus 32, and that's going to be equal to 8. So that is going to give us a formula C8H8O2. We can use that then to come up with a structure based off of the mass spec and or the NMR. Let's look at then what would be an exact skeletal structure for this compound. So we know that we have C8H8O2. And we have a carboxylic acid. So if you take away a carbon and 2 oxygens and 1 hydrogen here for the carboxylic acid, we would be left with C7H7. What's C7H7? Typically, that's going to be a very, very, very unsaturated compound. So what is possible for C7H7? We know one part of the molecule, carboxylic acid, and we know we have C7H7. That's about all the information we can get from here and here. Well, we can do one of two things. We can look at the mass spec and find out the fragmentation pattern and come up with a structure. And in this case, that's possible. Or we can use the NMR and pretty much come to the same conclusion if, they both correspond, of course. Let's look at the mass spec before we move on to the NMR, because this is kind of very obvious. So here we have 136 minus 118. This is a loss of 18. 18, is typically water, H2O. So this could be minus water. The next peak is at 91. So 136 going to 91 is 45 units. And we saw a lot of fragments that were 45. Knowing that it's a carboxylic acid, that makes it even more obvious. Now we have 65 and 28. 28 is typically, 28 is CO. And that makes sense because we have a CO here. Let's try to figure this out with the mass spec first. So if you have 91, if you add this up here, this is going to be 84 plus 7, and that's a 91. So that makes good sense here, 91. Carboxylic acid, if you add this up, 12 plus 32 plus 1, that is equal to 45. So that's probably what's getting off. So we have a C7H7 attached to a carboxylic acid. We have a 65 peak here. 65 is typically a breakdown of a benzene. So we can say that there is a benzene in here, and that is going to be 77 plus, 91 minus 77 is 14, and 14 is typically a CH2. So we have here a very nice mass spec that's telling us we have a benzyl group, benzyl cation. We have a carboxylic acid. And since you have a 77, it's mono-substituted. So this carboxylic acid has to be on the side chain. Because you have 5 hydrogens here, this is going to be C6H5. So it's not anywhere on the ring, it's on the side chain. So just from the mass spec, we can put these two pieces together and come up with a structure for this, where you have a benzyl cation or benzyl group directly attached to a carboxylic acid group. And you can see, we've done so many videos on fragmentation patterns. We can see how, you can take off this, and then you can have this benzyl cation expand into this. And that is going to give you your tropylium cation, which we talked about. So yes, that's your tropylium cation. And that is going to be your C7H7. So we have two pieces and we have put them together. And just from the mass spec and the infrared, we have come to this conclusion. We also have more information that's going to confirm that. Let's see if that's true. Let's tabulate this data here. Let's look at the NMR peaks here, tabulate the data like we've done before, A, B, and here's another peak right up here. It's offset because it's off the scale. It's 2.2 ppm in addition to the 10. So that's going to be 12.2 ppm. And there's only one thing and one thing alone that's that deshielded. Well, it's giving us a hint that that could be a carboxylic acid proton. Let's look at tabulate the numbers. Let's check the numbers out here. Peak A, B, and C are showing up at around 3.7, 7.2, and 12.2. So this is offset 2.2. That's 10 plus 2.2 is going to be 12.2. Number of hydrogens, let's measure it. Well, and then we'll do the multiplicity here. So this is going to be, in this case, 3 centimeters. Over here, this is 7.5 around, or 7.4 centimeters. This is about 3.1. And this is 1.5. Well, dividing by the lowest denominator here, this is approximately going to be, setting this to 1, this is about 2, and this is about 5. And let's see if they add up to the total number of hydrogens. That's going to be 8 hydrogens, which is what our mass spec is telling us. And so we'll just go with that. Let's look at the multiplicity. This is just a straight peak, no splitting. So that's a singlet. This has got lots of splitting. Let's put that as a multiplet. And the last one is kind of a broad singlet. And I'll just put broad here within parentheses. Broad singlets typically mean they're hydrogen bonded, and we could see how that could have a lot of hydrogen bonding. And number of neighbors. So let's look at the multiplicities here. N plus 1 multiplicity is a singlet, so therefore it's 1. N is going to be equal to 0. It's in an environment where it has no neighboring hydrogens. This is a multiplet, so we don't really know how many neighbors. This is again a singlet, so N is going to be 0, just like over here. So there are carboxylic acids. That is kind of understandable. You don't have any hydrogens on the atom next to it. So let's then put a structure together just based off of your NMR. You have a 7.2, which means you have a benzene ring. So this B would mean you have 5 hydrogens here, which means if you have 5 hydrogens, you only have 1 arm left to hold on to something, which would make you mono-substituted. And the splitting pattern kind of corresponds to that. Now, what's over here? We know from this data that you have a carboxylic acid. So this, I'm going to put a star here. This tells us that you have a carboxylic acid. What about this? Where does this come in? Well, let's see what's left. We have a benzene, and that is going to be C6H5. We have a carboxylic acid, and that is a CO2H. And here is a singlet with 2 hydrogens. And obviously, this is at 3.7. Therefore, it's probably in a very D-shielded environment. We have to put something here and something here. Well, and that should come probably in between, because we cannot have any other substituents on the benzene. Carboxylic acid is a cap functional group. That means you can't put it anywhere after this. So it should come in between here. Singlet, 2 hydrogens. So if you have 2 hydrogens on a carbon, that is going to be a CH2. So we can put all of these pieces together and come up with a structure. So you have this plus this plus this, a benzene that is mono-substituted with 5 hydrogens, which is why you're getting a multiplet there at 7.2. We have a CH2 in between, and we have a carboxylic acid following that. Phenylacetic acid. That's exactly what you got using your mass and your infrared. This was basically kind of corroborating our data here. So we know that this is the structure. Given the 3 spectra here, we are both coming to the same conclusion that it is phenylacetic acid. All right, guys, so hope that kind of brings to light some of the ways of putting spectra together to come up with a structure for your formula. or for your spectra. Talk to you soon. Bye.